Hello everyone, I'm Litao from Tsinghua University. I will talk about the status and the prospect of CDEX on behalf of the CDEX collaboration. Firstly, I will give a brief introduction to direct detection of dark matter and our CDEX collaboration. Then I will talk about the recent status of CDEX1 and CDEX10, mainly focus on the physics analysis progress. Then is the future prospect of CDEX at CDPO2 and the key technologies R&D. Finally, I will summarize my talk. As we know, dark matter accounts for about 27% in our universe. But until now, we don't know what dark matter is. There are three kinds of approaches to do dark matter searches, including the direct detection in the underground laboratory, and the indirect detection with satellites outside the Earth, and the accelerator to make dark matter. In direct detection, we can measure the recoil spectrum from elastic scattering. It is a time-integrated analysis. Also, we can measure the modulations of the counter rates, which is a time-related analysis. According to different modulation period, it can be divided into annual modulation and diurnal modulation. The third one is direction detection, which requires good angular resolution for the detectors. Both of them need lower background, lower energy threshold, and larger exposure. CDEX collaboration was formed in 2009. Now is composed of 11 institutions and nearly 80 people. The key technology is p-type point contact germanium detectors, which is a kind of semiconductor detector working at the liquid nitrogen temperature. PPC germanium detector has many advantages. For example, the crystal is super pure, so the internal background is very low. It has a very good energy resolution and the scalability for more target mass, and so on. The physics targets of our CDEX include the direct detection of light dark matter and neutrinoless double beta decay searches. There are many phases in CDEX. CDEX1, CDEX10, CDEX50, CDEX300 new. Different target mass for different phases. Now we have finished the CDEX1 and near the end of CDEX10 phase. Next, we will build 50 kilogram germanium detector arrays for dark matter searches, and 300 kilogram enriched germanium detector arrays for neutrinoless double beta decay experiment. CDEX are carried out in the world's deepest underground laboratory, CGPL. The muons background here is very low, measured to be about 60 muons per square meter per year. The details of CDPL status can see Professor Hauma's talk on August 30. In the first phase, CDEX1, we have two 1 kilogram PPC germanium detectors, CDEX1A and CDEX1B. We have constructed the passive shielding with low background lead, high purity copper, and polyethylene. A sodium iodide detector surrounding the germanium detector worked as the veto detector. CDEX1 experiment was located in the polyethylene room at CGPO1. Based on CDEX1A, CDEX1B upgraded the GFET with lower noise and lower background materials. It runs totally over than 4 years. The analysis threshold of CDEX1B is lower to 160 eV, which improved and extended the sensitivity to 2 GeV. The second phase is CDEX10. We have 3 strings germanium detector. Each includes 3 germanium detectors. The germanium detector is sealed into the vacuum chambers, then immersed into the liquid nitrogen. In this phase, we want to study the performance of germanium detector immersed into the liquid nitrogen. And this phase is very important for the future 100 or ton scale experiments. Based on about 100 kilogram day exposure, we published its first result on 2018. The analysis threshold is 160 EV. The background level is 2 CPKKD at 224 keV. And we give the strongest limits on the spin-independent cross-sections at 4 to 5 GeV. Beyond the traditional WIMP nucleon spin-independent analysis, we also adopt many models and carried out many more analyses with our experiment data. First is anti-modulation analysis, which can provide smoking gun signatures for WIMPs independent of the background modeling, while only requires the background at a relevant energy range is stable with time. With 4 years data from CDEX-1B, we carried out the model-independent analysis and the model-dependent analysis. We didn't find any signature of any modulation from our data, and we excluded the cogent signal region. Also, Dama's phase 1's interpretation with the WIMP spin-independent interaction under the Standard-Hello model in germanium crystal. Those results also correspond to the best sensitivity below 6 GeV among anti-modulation measurements to date. Another is the Magdal effect, which has been hotly studied and discussed in recent years. We adopted the Magdal effect model and carried out the time-integrated analysis and the anti-modulation analysis. The sensitive dark matter mass window are expanded to 50 MeV, about 1 order of magnitude to lower WIMP masses. Finally, we give leading results at 50 to 180 MeV. We also presented improved results on solar axion and Victor bosonic dark matter based on CDEX-1B data. We developed the profile likelihood ratio method for CDEX data analysis in the presence of backgrounds. All the constraints improved over our previous results, especially leading sensitivities were reached below 800 EV for germanium-based experiment. The data from CDEX-10 germanium detector array were analyzed to search for solar dark photon and dark photon dark matter. No significant signals were observed. This analysis proved the new parameter space both for solar dark photon and dark photon dark matter. For the solar dark photon, the leading sensitivity had been given at mass range of 10 to 300 EV. Recently, we reported new results on WIMP searches under effective field theory. The non-relativistic EFT approach and the Carroll EFT approach are adopted. We set limits on the coefficients of 14 EFT operators and limits on the scalar Weber-Pion couplings. The next step of CDEX is to adopt a 50 kilogram germanium detector array immersed into the liquid nitrogen directly. Here is a concentric map. It is composed of 5 strings, and each string including 10 germanium detectors. The total target mass will reach about 50 kilogram. In CDEX 50 phase, the background level will be controlled to be 10 times minus 2 CPKD at 1 keV. The energy threshold for data analysis will be 100 EV. With an exposure of 50 kilogram years, the WIMP spin independent sensitivity will reach 10 times minus 44. Beyond the WIMP searches, multi-physics channels will be analyzed, including axions, dark photons, and so on. Towards to those targets of next stage, many K technologies must be well method, such as the germanium crystal growth, germanium detector fabrication, ultra-low background electronics, ultra-pure underground e-forming copper, and so on. To further reduce the background from vacuum structure, we developed the bare germanium detectors immersed into the liquid nitrogen. This picture shows the bare germanium detector testing. With the ASIC preamplifier made by ourselves, it can work well in liquid nitrogen and has a very good long-time stability. To reduce the background from the electronics and further lower the energy threshold, we are developing the ASIC preamplifier with different substrate and cables. Now the electronic noise can be well controlled to be less than 26 electrons. The details can be found in this paper. To control the cosmogenic radioactivity in the copper structure, we built an underground e-forming copper production prototype. Here is a picture of the facility at CDPO1. We also established the purity assay procedure by ICP mass. According to our simulation, radon in the liquid nitrogen will be a dominant background if it cannot be well controlled. We have set up a radon enrichment prototype and a measurement procedure with a liquid scintillator detector. Now the commission measurements are ongoing. For the detectors, we will cooperate with the commercial companies with the strict cosmogenic background control during the fabrication. At the same time, we are developing the homemade germanium detectors. Hope we can set up a fabrication facility in the underground laboratory in the near future. CDEX1 and CDEX10 were carried out in CDPL1. For next stage, large detector array, we will move to CDPL2, which has a volume of 300,000 cubic meters, and there will be 8 main halls. An additional pit had been prepared for next generation CDEX experiment at the C1 hall. In this pit, a large liquid nitrogen tank had been built. The liquid nitrogen has a diameter of 30 meters and a height of 30 meters. That is to say, for the germanium detector array at the center, there is at least 6.5 meter liquid nitrogen as shielding and cooling. The design background at the liquid nitrogen center will reach 10 times minus 4 CPKKD at 1 keV and 10 times minus 6 CPKKD at 2 MeV. The construction of liquid nitrogen tank has completed, and a steel working platform has been constructed in last October. CDEX 50 is under technical design, and the report will come soon. Here is my summary. CDEX uses unique advantages of germanium detectors for light dark matter search at CDPL. Recently, we have published many leading results for low mass dark matter with multi-physics channel analysis. We have started the CDEX 50 experiment, which will located in C1 hall of CDPL2. Many key technologies R&D are ongoing and have made very good progress. That's all. Thanks for your attention.